Alright, so we finished up Chapter 5. We have this one lesson from Chapter 7 and then a couple from 6 and we're done. So the first thing we want to talk about here is, this goes back to limits, but if you're wondering why we didn't do this in the limit chapter, it's because we're going to be taking derivatives to help us find limits. So before we get started, let's take 0 divided by a number, and remember that 0 divided by a number is okay, it equals 0. But a number divided by 0, no, we can't do that. That's undefined. Okay. So when we try to take a limit, if we end up with 0 over 0 or infinity over infinity or any of these other forms after direct substitution, those are called indeterminate. Those are indeterminate answers. So sometimes there are things we can do listed here on these pages to deal with that, but sometimes those things don't work. And when they don't work, we can use L'Hopital's rule. Now sometimes also some with an S, L'Hospital, sort of. It's French. But so don't think it's a typo. So I've had students freak out. They're like, oh, they spelled it wrong. It's spelled both ways sometimes. So anyway, so if we have this limit where we have a ratio rational expression, and when we do direct substitution, if we get one of these cases, and we're going to focus on these two, then what we can do is we can take the derivative of the numerator and the derivative of the denominator and see what happens, as long as the derivative does not equal 0. Okay? So when you do this, if you try to use this rule all the time, you may get something that's wrong. So always check direct substitution first and make sure you get one of these. So it's going to be a two-step process. And the second warning here, well, this is only use this for these, and this warning is, this is not the quotient rule. So when you see this, don't use the quotient rule on that when you see that limit in front of there. Okay, so if you think about it, if we have the function, although that kind of went straight, it shouldn't have went straight up, and we have the derivative, and the limit of the derivative should match the limit of the function, basically. Maybe not universally, but okay. So these first three examples, we want to do the problem the old way and the new way. Now the thing is that sometimes there is no old way. We have to use this. But on all three of these examples, they can be done two different ways. So the old way, hopefully when you look at this, you kind of can, I know it was a long time ago, but this is going to be the dividing out technique. So we're going to factor the difference of two squares in the numerator. And I guess I didn't really need parentheses there, but so if we use the dividing out technique and we do that, we're left with the limit as x approaches 2 of x plus 2. And now we can use, so we could not use direct substitution there, because we would have got 0, 0. Actually, I'm going to show that in a second. So now we can use direct substitution. 2 plus 2 equals 4. Okay, so that's the old way. Now we're going to look at the new way. So the new way would be always check direct substitution first. So you would have 2 squared minus 4 over 2 minus 2. Which would be 0 over 0. Check. Once you've established that, and it's very important that you establish that first on the AP exam, on the free response part of the test, you need to show that. Okay. Now what we can do is we can take the limit as x approaches 2, and we can take the derivative of the numerator, which is 2x, and we can take the derivative of the denominator, which is 1. It's not the quotient rule. Now if we use direct substitution, we just have 2 times 2 over 1, which is 4. Okay? Very important you check that first there. Okay. So now, the old way. The old way would be to say, okay, this is a trig limit, and it's one that's pretty close to one that we're supposed to have memorized. So we have that 2 out there, so we can have 2 times the limit as x approaches 0, and we can move that 2 inside here. Now, this matches up, technically, so now this matches up with something we're supposed to have memorized. So we're supposed to have this limit memorized when we have sine of an angle divided by the angle, that equals 1 when x approaches 0. So we would just have 2 times 1, and that would be 2. Okay? So the new way, if we plug that in there, we would have the sine of 2 times 0, which would be the sine of 0 over 0, which is 0 over 0. Okay, you must check that. And so now we can take the derivative of those. So the limit as x approaches 0, the derivative of sine is cosine, but we have to use the chain rule. So we have to multiply by the derivative of the inside, which is 2, and the derivative of x equals 1. So now we have 2 times the cosine of 0, which is 2 times 1, which is 2. And we get the same answer. And you say, well, why are we doing this? Well, first of all, we're reviewing our limits, and second of all, we're just showing that it works both ways, because soon there will be no way over here, and we will have to use this. Okay, so now, when you see that limit with the square root, one of your first thoughts should be that that's probably rationalizing the numerator. Now, it's been a while since we've done that, so this is good review. You could pause, as always, in all the notes, you could pause and try to do them yourself. Would be better. So, to rationalize the numerator, you multiply by the conjugate. Hopefully you remember that word. Let's write it in there anyway. Conjugate. Okay, so if we multiply that out, we're going to get x, and then minus and plus, that's canceled. That's why we're doing that, and then we're going to get minus 1. Now remember, in the denominator, do not multiply that out, okay, because these are going to cancel. That's why we're doing the rationalizing the numerator there. And x approaches 1. Don't forget this is a 1 in the numerator. So now we can use direct substitution here and have 1. The square root of 1 is 1. 1 plus 1 is 2. So that equals 1/2. Okay. Now, the new way, we would take the square root of 1 minus 1, direct substitution. All of these turned out to be 0 over 0. That's a little awkward, but okay. So now we would take the derivative of the numerator, which would be 1/2 x to the negative 1/2. And we'd take the derivative of the denominator, which would be 1. Okay, so if we rewrite that, that's going to be 1 over 2 square root of x, and x is approaching 1. So that is 1/2. Okay, so if you remembered all of those old ways, then that was a little bit boring for you, but I still think that that review is good for us. Okay, these are relatively short notes too, just 2 pages front and back, or one front and one back. Okay, so down here we have this, it's trig function, so you might think, well, maybe it matches one of those. We did have another one with cosine. We do have a single term down here. Maybe we could split those, but none of that is really going to work. So if you tried some of that stuff. So if we do direct substitution, we have this. And that's 1 minus 1 over 0. So that's 0 over 0. Okay? So we can take the derivative of the numerator. So the derivative of 1 is 0, and the derivative of sine is cosine. Now, there was already a negative there, so it just stays there. Now, the derivative of cosine is negative sine, or the opposite of sine. So those are going to cancel out. Now we can substitute that in there, so we're going to get cosine of pi over 2 over sine of pi over 2. So the cosine of pi over 2, we just did that up here, that's 0. Sine of pi over 2 is 1. So that equals 0. So for some reason students get thrown off by that and they're like, I don't know, it's just 0. That's why I put on the top of the page. 0 divided by a number is okay. 0 divided by 1 is okay. It's 0. Okay. Now, let's try this one. So if we use direct substitution, that's 2 minus 2 and 2 minus 6. So that's 0 over negative 4. That's just 0. We're done. Okay. Now, what happens if, you probably shouldn't even write this down. Don't write this down. Maybe, I don't know, it's up to you. What if you would have tried to use L'Hopital's rule on that? You would have said the limit is x approach 2. If you take the derivative of that, you get 1. If you take the derivative of that, you get 1. That's just 1, so that would be 1. But that's not correct. So this is what we're trying to tell you. You have to check first, which we did on all 5 of those. We checked those. Okay? And I'm pretty sure that on the AP exam it took off a point if they didn't check for that. Okay. So, that's nice. Moving to the next page here. Let's try some of these out again. So, 1 minus the cosine of 0 over 0 squared. 1 cosine of 0 is 1. 1 minus, that's 0 over 0. Check. Make sure you do that step first. Okay? Oh, this is something I remember. Okay, this is really important. What am I going to highlight this in? Okay, you must show the ratio of the derivatives. Okay, this is what they took off for on the AP exam. Okay. You must show the limit of the derivatives. Okay. Where do I write that? Must show the limit of the derivatives. So important. That's, I mean, obviously I'm making a big deal about that. It's a big deal. It just popped into my mind. I remembered what they wanted. They did not, I think they lost 2 points if you didn't have that step. I think they took it all, maybe. Alright. So, back to this problem. Here we go. The limit of the derivatives. The limit of the derivatives. So the derivative of 1 is 0. The derivative of negative cosine is, so the derivative of cosine is negative sign, but we have a negative here, so that's going to be positive sign. Now, the derivative of x squared is 2x. So now, again, limit of the derivatives, show that step. So the problem, though, is when you plug 0 in there, you get 0 over 0 again. So you do it again. You do it again. So we have the limit as x approaches 0. The derivative of sine is cosine. The derivative of 2x is 2. Now, when you plug 0 in there, you have cosine of 0 over 2. Cosine of 0 is 1. So that's 1/2. Okay, so you do it again. Okay, looks like a lot of stuff up here. But if we plug in 0, we're going to have the square root of 1 minus 1 minus 1/2 times 0, which is just 0 over 0 squared. So that's 0 over 0. Check. Alright, so the limit of the derivatives, the limit of the derivatives, the limit of the derivatives. So that's going to be 1/2, 1 plus x to the negative 1/2 minus 1/2 all over 2x. Okay? So that if I plug 0 in there, is 1/2 minus 1/2, which is 0 over 0. So I get 0 over 0 again. So I go again, do it again. So that's going to be the limit as x approaches 0. So now that's going to be negative 1/4, 1 plus x to the negative 3/2. Now be careful here. I didn't have to use a chain rule because the derivative of the inside is 1, but be aware that we may have to do that. And then the derivative of 1/2 is 0, so that's gone, and the derivative of this is just 2. So now we should be okay. So plugging in 0 here, that's just 1, so whatever, that's just going to be 1. So that leaves us with negative 1/4 over 2. Now, I'm going to treat that as a complex fraction, so I'm going to multiply that by 4 over 4. So that's going to give me negative 1/8. Alright. Well, I switched to blue there, but... Okay, so if we plug in infinity, oh, we're finally going to get infinity over infinity. That's nice, finally. To the 50th power, that's going to be infinity over infinity. Finally, first time, I think. Okay, so we need the limit of, I guess I could have, well, we had that twice over here, so. Obviously, I'm highlighting this every single time. It's a big deal. So if we take the derivative of e to the x, the derivative of e to the x is e to the x, and the derivative of this is going to be 50x to the 49th as x approaches infinity. Now, if you plug infinity there, you're going to get infinity over infinity again. Okay, so we need to think about, I don't have room to do this as many more times as we're going to need to do this. So if we keep going again, dot, 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 and again, and again, and again. Okay, so we're going to get the limit as x approaches infinity. We're going to keep doing that. Well, the numerator is always going to be e to the x. If you think about the denominator, that's going to be, so the next time it's going to be 50 times 49 times x to the 48th. And then if you do it again, you're going to keep bringing those down, so hopefully that would be 50 times 49 times 48. So hopefully you get it, that's going to be 50 factorial. Okay? Now, that's a pretty big number, 50 factorial, but when we plug in infinity, we're going to have e to the infinity over 50 factorial. And no matter how big 50 factorial is, it's not infinity. It's a number. So that's going to stop at some really big number, and this is going to keep going. So that's going to give us infinity divided by 50 factorial, which is going to be infinity. Okay? Alright. Now, this one is a bit tricky. So I'm going to do it with a graph. So if you think about the natural log, the graph of the natural log goes something like that. Okay? And the graph of cosecant, cosecant goes with sine. So you would start with the graph of sine, and then you would put little parabola looking things off of the tops and bottoms. That should be a dotted line where I don't know if it looks like a dotted line or not. Yeah, it kind of does. Alright. Okay, so if you think about that, as x approaches 0 from the right, the natural log approaches negative infinity. And if you think about cosecant, as it approaches 0 from the right, that approaches positive infinity. Now that's basically infinity over infinity. We can factor the 1 out, or the negative 1, so that works for us. Okay. Now, we need the limit of the derivatives. So as x approaches 0 from the right, so the derivative of that is 1 over x. and the derivative of cosecant is negative cosecant cotangent. Okay, so if we think about what that looks like, that's going to be negative 1 over x, and 1 over cosecant is sine, and 1 over cotangent is tangent. So these trig functions are a little bit more common to us, a little bit more comfortable than these. We're used to them, dealing with them a little bit more, so we would want to make that change there. So if we want to take the limit here, so first of all we can do a couple things here. So we can factor out the negative, then we can look at the limit as x approaches 0 from the right. Now we can put these two together, sine x over x, and then we can multiply by the limit as x approaches 0 from the right of tangent. Okay, so the 0, so this limit approaches 1. And the limit of tangent, as tangent approaches 0 from the right, the graph of tangent looks like this. So as we approach 0 from the right, that approaches 0. And maybe you knew that already, but alright, so that's 0. Now you notice that one's not highlighted. I wouldn't expect something like that on the AP exam, but a little bit tricky there. Okay, let's wrap this up. So last two examples here. The L'Hopital's rule does not, oh there I put the S in on that time. So on the other side I left the S out, and this time I put the S in so you could see it both ways. That's probably, oh you made a mistake. Yeah, no I did. I do sometimes, but that's not one of them. Okay, so what we can do if we have a product and it gives us the 0 situation is we can rewrite it as a quotient. Right, so this is a complex fraction. If we multiply by g of x times over g of x, then we would get back here. Okay, so if we take the limit as x approaches 0 from the right, and we rewrite this as x over 1 over the natural log of x. Now, if you let that be 0, that's going to be 0, and this is going to be 1 over, and we just talked about how that approaches negative infinity. So 1 over negative infinity is 0, so that's approaching 0 over 0. So now, don't forget to write the limit of the derivatives. So now the derivative of x is 1, and the derivative of the natural log is 1 over x. And that's getting to be pretty fraction crazy there. So we could just treat this, and so we could multiply that by that's going to be so if we multiply this by x and this by x, this is 1 and this is x over 1, which is just x. And then if we plug 0 into that, that's just 0. Okay? And this last one, we can do the same thing. So if we plug in infinity, we would have negative infinity e to the negative infinity, which would be negative infinity over e to the infinity, which would be negative infinity over infinity. So we can do L'Hopital's rule. But first we need to switch that to a quotient. So as a quotient, we could rewrite that as x over 1 over e to the x, because that would get us back to here. Okay, so now if we take the derivatives, don't forget to write the quotient of the derivatives, so that would be 1, and this is actually e to the negative x, so the derivative of that's going to be e to the negative x times, right, it's e to the u times du, and du is negative 1. So that's going to be negative e to the negative x. Now, if we plug negative infinity in there, we're going to have 1 over negative e to the infinity, which is infinity, so that's going to be 0 also. So a few of these came out to be 0. Okay, and that's a Valentine's Day cartoon for you. I know it's a little bit ahead, but I like it because it has exponentially. So that's about that time. And all that's left is a couple lessons of chapter 6. So let's hang in there and get this done.